So this is, I've slightly changed the title from the one in the program. In the time available, even less time now, I thought I'd better concentrate on one aspect, which will be the logical aspect. And this, I should say, is joint work with Rui. So I'm going to focus on the logic of contextuality, which is really going back to Koch and Specker in their original vision of their famous. We heard about, obviously, about the result earlier in Ottfried's talk. So let's take as a starting point the sort of usual idea that if you look at the formalism of quantum mechanics, the kind of impediment to a classical view is non-commutativity. And one way of making this precise is that we can do physics in terms of C-star algebras. I mean, with we can do classical physics in terms of commutative C-star algebras. And by Gelfand duality, these are function algebras on topological spaces. So with a little stretch, we can think of the spaces as the configuration spaces, and then we have observables in the classical sense. So that's where everything commutes. And quantum physics, as we know, lives in general non-commutative C-star algebras, which is essentially subalgebras of operators on a Hilbert space. So this is the difference between commuting and non-commuting. And we can distill the essence of the difference further, and this was already done by von Neumann, who founded the mathematical formalism of quantum mechanics that we're still using today. We can focus on the projectors, which play the role of basic propositions or properties. And of course, we can build more complicated things from projectors. And although nowadays we look at sort of issues with noise and unsharp measurements by dilation and so on, we can still think of this as fundamental ingredients of quantum mechanics. And if we focus on the projectors, this gives us the original, what Birkhoff or Neumann moved to quantum logic. Now we can say that quantum logic, particularly if we think nowadays of working quantum information and quantum and computation, and if we also think of the way that foundations is done nowadays, so quantum logic hasn't perhaps been such a success. And perhaps one of the reasons, as admitted by von Neumann from early on, is right at the beginning, there's an issue with the physical interpretation of the logical or algebraic operations on non-commuting projectors. Obviously, projectors correspond to closed subspaces of a Hilbert space. And it's perfectly fine if you look at subspaces to take the intersection, whether or not the corresponding projectors commute or not. The problem is, does it really have a good physical meaning? So if you go down the path of saying that you include those, then that's the traditional quantum logic path. But Koch and Specker did something different. And they represented non-commutativity and hence incompatibility, hence essentially non-classicality by partiality. In other words, if it doesn't make sense to combine things, don't combine them. And it turns out that although this seems very weak, this was exactly the basis on which they derived their result. And this leads to their notion of partial Boolean algebra. So I'm going to go back to their way of formulating their result. Nowadays, people just, sort of have a more direct way of talking about these ideas, as we heard, for example, in Ottfried's talk. But this is going right back to the way they looked at it in terms of partial Boolean algebras. They were actually both, they're both logicians. So a partial Boolean, we all know what a Boolean algebra is. This gives us the event spaces for classical probability with some issues about various kinds of completeness. So a partial Boolean algebra is given by something that looks like a Boolean algebra, but where the binary operations of conjunction and disjunction are taken to be partial. And their domain is given by a certain symmetric binary relation, which we think of as co-measurability or compatibility. And these must satisfy the following property. Every set of pairwise commensurable elements must be contained in a larger set of pairwise commensurable elements, which form a Boolean algebra under the restrictions of the given operations. So if you start with some commuting projectors, you can expand them up, closing up under their products and so on, and you'll get a Boolean algebra of commuting projectors. These are, so to speak, these would be the contexts in terms of the usual discussion. So for emphasis, I'll always say total Boolean algebra when I mean the standard notion. Boolean algebra when I mean total Boolean algebra. When I mean partial Boolean algebra, I'll say partial. And of course, the key example is exactly projectors on a Hilbert space. So we all know what a projector is, idempotent and self-adjoint operators. And the operation of product of projectors becomes a partial one, which is only defined on commuting projectors. So this seems very weak. And yet it turns out to be, in fact, in many ways, a sufficient basis as a foundation of the whole of basic quantum theory. And of course, we have a notion of morphism of partial Boolean algebras, which are maps preserving commensurability and the operations wherever defined. So this is the world of partial Boolean algebras. Now, what did Kochen and Specker show? What they actually showed in their famous paper is that contextuality is inherent in quantum mechanics, even in finite dimension, as soon as the dimension is at least 3, and moreover can be formulated in logical terms using this notion. So what did they, oh dear, yeah, we didn't need that. Yeah, okay, so the original formulation was, we might, given a partial Boolean algebra, we might say that this partiality is just a game, and maybe we could, if we really wanted to, make all the operations total. So their original formulation of contextuality was that you had a partial Boolean algebra of projectors, which really was partial, and there was no embedding of it into a total Boolean algebra as soon as a dimension of H is at least 3. And in fact, they consider the hierarchy of increasingly weaker forms of non-contextuality, hence whose negations form increasingly stronger forms of contextuality. By the way, I suspect that although everyone references the 1967 paper and the various other papers that they wrote, few people read them, and I highly recommend them to be as very interesting reading. So here's you can embed A in some Boolean algebra, that's the sort of weakest kind, the strongest requirement for non-contextuality is embedding, and the weakest kind is just that there's some homomorphism into some Boolean algebra. Now, remembering that the two-element Boolean algebra plays a special role, just the Boolean algebra 0, 1, the sort of truth values, classical truth values, then the first condition is equivalent to say there are enough homomorphisms, two-valued homomorphisms, to separate elements of the partial Boolean algebra to distinguish them. And the third is equivalent to there is some two-valued homomorphism. So if we take the contraposition and ask for the strongest failure of non-contextuality, therefore the strongest contextuality property is that there is not even one homomorphism, two-valued homomorphism from A into 2. And this is what Kochen and Specker prove for P of H when the dimension of H is at least 3. And we shall call this the Kochen-Specker property of a partial Boolean algebra. Now, there's a paper by George Boole, obviously the person who originated Boolean algebras, which talks about the conditions of possible experience. Another beautiful paper, well worth reading, incidentally, from the 1850s, which, as Pitofsky pointed out, actually is a precursor of the whole discussion of Bell inequalities. And Pitofsky has a beautiful paper about this. So really, Bell inequalities are giving the conditions of possible classical experience. And we can say that what the behavior we see manifested by the partial Boolean algebras of quantum theory are giving us conditions of impossible experience in a suitable sense. So here is what I think is a physically remarkable result from Kochen and Specker, which is also from that paper, which says that the following are equivalent. The partial Boolean algebra is Kochen-Specker, and there is some propositional contradiction, a propositional formula, logic formula, or if you like, a Boolean algebra expression, which, however you assign truth values to the variables, will be false. So it's a contradiction, or you can even prove that it's equivalent to false. And there is an assignment to its variables of elements of the partial Boolean algebra such that it evaluates to true. So in Coach and Specker partial Boolean algebras, contradictions can be made true. I find this a rather fascinating thing. And by the way, one interesting question I'll mention hopefully briefly at the end is to characterize which are the contradictions that can be made true in quantum theory. I don't think there's any general description of that at present. And we know that there are some contradictions that can't be made true in this sense. We know there's always something, but what's the general, how contradictory can you be, or what kind of contradiction can you have that's verified in quantum mechanics? And of course, what this is telling us is this event algebra cannot be interpreted globally in a consistent fashion. Our local observations, real observations of real measurements, of course, make sense locally, but they cannot be put together globally by reference to a single underlying objective reality. The values that they reveal are inherently contextual. And this is really another take on the my favorite slogan about contextuality being about local consistency and global inconsistency. And of course, there's an ongoing debate, philosophical, perhaps reaching into more applied things about how the world can be this way. Okay, well, now we get to something more technical. There was a very nice paper by Chris Hernan and Benno van der Burg, which showed that every partial Boolean algebra is the co-limit of its Boolean subalgebras. So co-limit generalizes the idea of taking a union of a family of subalgebras and piecing them all together into a single algebra. And it's a fact that if you can look at the context, the Boolean subalgebras, things that look perfectly classical in themselves, and if you can piece them together where you don't, in a way that doesn't necessarily, I mean, where you end up then with a partial Boolean algebra as the co-limit. Now, co-limits there are two main cases for co-limit. One is co-products, which is a simpler thing. It's just putting together two disjoint algebras side by side. And co-products of partial Boolean algebras have a very simple direct description. You take the disjoint union and then you identify the zero element and the one event. And other than these identifications, no commensurability holds between elements of A and elements of B. So it's a very simple construction, actually much simpler than the description of co-products in Boolean algebras, where of course everything has to be compatible. So you can start forming Boolean combinations of elements from A and elements from B. Now, the general case of co-limits, so one of the contributions in our paper, which may not be so much to the taste of or to the interest of people here, is an explicit construction of how you build these co-limits. The main thing is to know what the result says, because we're going to use it a lot. So we use this. So what we're going to do is to prove a following result, which tells you how to take a given partial Boolean algebra and then throw in extra compatibility relations and then get another Boolean algebra in a sort of free or with minimal assumptions kind of way. And this is already taking us in, as we'll see, hopefully, in the direction of the exclusivity principle. So given which, so to speak, allows us to reach beyond the context that we currently have and find additional things that can be put together. So here's the result. I'll state it. Given a partial Boolean algebra and an arbitrary binary relation, we can extend the partial Boolean algebra from A to this A extended with circle dot. We can sort of embed, if you like, the original partial Boolean algebra into this extended one, and this has the correct universal property. For any other partial Boolean algebra that does make these things compatible, then it factors through this embedding. And if you if you're interested in such things, then a nice point is that this result can be proved constructively. I don't think that's to the interest of most people here, but I mean, there's a paper and there are details here. I mean, just to show you the construction, I mean, it's an inductive construction. The reason this is not trivial is because we're dealing with partial algebras, and partial algebras are always tricky. So there's an inductive construction where we simultaneously define when things are defined, when they're equal, and when they're compatible. Everything has to be thrown in the mix together. Now, as soon as we have that, then we can immediately vary this construction and get the sort of other thing we need to show that we have co-limits, which is technically co-equalizers. I'm glossing over this because I guess most people aren't so interested. But the main thing to remember is that we have this ability to freely extend a given partial Boolean algebra with additional compatibility relations. Now, you might get worried at this point because we know, as we just said, that every partial Boolean algebra is a co-limit of its Boolean subalgebras. But of course, we could also take the co-limit of the same diagram of Boolean subalgebras among the Boolean algebras. And then, according to our result, there should be a morphism from A to B. And we just said that the Cauchy-Specker theorem is saying there's no morphism from these bad or good or Cauchy-Specker partial Boolean algebras to any Boolean algebra. So aren't we contradicting ourselves? And the reason we aren't is that is that something that people working in Boolean algebra often banish from consideration is something that's really there. And that is the one element Boolean algebra where 0 is equal to 1. They don't like this, of course, because it's the contradictory logical theory. And of course, the one element Boolean algebra doesn't have a homomorphism to 2 because it has to send 0 to 0 and 1 to 1, but 0 equals 1. So what that's telling us is that a partial Boolean algebra with the Cauchy-Specker property, when you take the co-limit of its diagram of Boolean subalgebras, that must collapse to the one element Boolean algebra, which already shows you that there was something non-trivial going on in that construction we were showing. So in fact, we can even make this a result. We can say that in fact, having the Cauchy-Specker property is the same as the co-limit of its diagram of subalgebras being this one element algebra. So you could say that the diagram is implicitly contradictory, and in trying to combine all the information in a co-limit, we obtain the manifestly contradictory one element Boolean algebra. But the interesting thing is that this is in the world of total Boolean algebras. And the interesting thing about a partial Boolean algebra with the Cauchy-Specker property is that it holds this implicitly contradictory information together in a single structure, a highly non-trivial structure. We'll see later just how non-trivial, well, we know that P of H is a very rich structure, and we'll see some striking features of that. So the point about quantum theory, we could say, is that it sort of embraces and contains implicitly contradictory information if we try to put everything globally or holistically together without actually being contradictory. So it's right on the borderline. Okay, so now let's come to tensor products. Tensor products are a weak point of traditional quantum logic. That's the main reason why there hasn't been a good interaction between traditional quantum logic and quantum information and computation, in my opinion. But anyway, that could be discussed, of course. Now, the Cauchy-Specker property arises in P of H when the dimension is at least 3. And it's instructive to actually write down the simple explicit description we can give of the projectors on single qubit space C2. In terms of what we've already said, you can write it down quite explicitly, although it's big, as a large co-product of 4-element Boolean algebras. Because as soon as you have one projector, then it has a uniquely determined orthogonal projector in 2 dimensions, and it won't and you get an orthonormal basis, and it won't overlap with any other orthonormal basis. And you just need to have enough of those, continuum any of those, and that is a complete description of P of C2. Now, the fascinating thing is this. A key point at which non-classicality emerges is going from P of C2, which obviously does not have the Cauchy-Specker property, to P of C4, which does. And P of C4 is, of course, just the tensor product of 2 copies of C2. I mean, I'm going to C4 because I'm emphasizing the tensor product here. So this poses the question, can we capture the Hilbert space tensor product in logical form? If we could do that, then I think we would be able to have a logic of contextuality that was really useful for the purposes of quantum information and computation, and would, I think, have many other interesting connotations in quantum foundations as well. So on the technical level, we're saying, is there a monoidal structure on the category of partial Boolean algebras such that we have a a way of going from a Hilbert space H to its partial Boolean algebra P of H, and it's actually functorial if you choose the morphisms carefully. And what we're saying is, can we make it strong monoidal? Can we find a product on partial Boolean algebras such that that product of P of H and P of K is the same thing as P of H tensor K? And this seems to be a hard problem, and I'm reporting some partial results towards it, and interesting ideas that have been suggested by it, but not a complete solution. But as I say, I think the positive answer to this question would offer a complete logical characterization of the Hilbert space tensor product. Okay, okay. So there was a first attempt by Hernan and van der Berg, actually also by Simon Kochen in a 2015 paper, essentially the same thing, which sort of takes the co-limit of the family of co-products of Boolean subalgebras as total Boolean algebras. So we can, I mean, this is a bit like in a Bell scenario, we can freely combine Alice's context with Bob's context, if you like, but put in a suitably general form. So the tensor product is not constructed explicitly in what they do, but actually we can give a simple, I mean, showing the sort of versatility of the construction I mentioned earlier, we can describe it by taking the very simple co-product and then extending it by the relation that makes everything in A compatible with everything in B. You think about Alice and Bob, all of Alice's measurements are compatible with all of Bob's measurements. So this is just what we're doing here. So we can do that, but it's by no means gives us the thing that we want. We can certainly get technically a Lax-monoidal functor. We have an embedding of P of H tensor P of K into P of H tensor K, where you just put in the projectors on the components in the obvious fashion. But it's easy to see that this embedding is far from being surjective. In fact, we're just using the Kochen-Specker theorem because we already said there are lots of two-valued homomorphisms on A tensor A. In fact, if you remember this description of C2, you can choose any homomorphism you like for each I on the 4-element Boolean algebra and then just simply paste them all together and you'll get a two-valued homomorphism. So you have uncountably many two-valued homomorphisms on P of C2. On the other hand, there's no such homomorphism on P of C4. This is sort of version of the four-dimensional version of the Kochen-Specker theorem. Now, in Simon Kochen's 2015 paper, it actually gives a beautiful argument showing that the images of P of H and P of K for finite dimensional H and K generate the whole of P of H tensor K, which is actually a very interesting result. He uses it to justify the result contradicted by the previous paragraph. And the gap in the argument is that there are more relations that hold in P of H tensor K than in this simple tensor product on these two partial Boolean algebras. So the question is, what are the extra relations? And bearing in mind that it's not just equations, it's also compatibilities and definabilities, as was shown in our inductive construction. But this result is very suggestive. It poses a challenge of finding a stronger notion of tensor product. Now, Etty, I know I started late, so realistically, when should I finish?
Well, if you finish within 5 minutes, it would be great.
Okay, I'll certainly, please stop me if I got to 4.5 minutes. I do apologize for having messed things up early. Okay, so what we want to do is find a more expressive tensor product that will reflect more of what's going on in the Hilbert space tensor product, and therefore this emergence of non-classicality. One of the weaknesses of the tensor product we already described is that if a term is kind of well-defined, then its subterms can also be shown to be well-defined. But actually, this is too strong a condition. It doesn't capture everything that's going on in P of H in general. And to see why this is an issue, consider projectors just written as simple tensor products of projectors, say, on P of H and P of K. To ensure that they commute, we need the conjunctive requirement that P1 commutes with Q1 and P2 commutes with Q2. However, of course, if they're orthogonal, then they trivially commute. And to be orthogonal, we have a disjunctive requirement, either P1 orthogonal to Q1 or P2 orthogonal to Q2. So if we establish orthogonality in this way, we're entitled to conclude that these things are co-measurable, even though, say, P2 and Q2 are not. And the idea that propositions can be defined on quantum systems, even if sub-expressions are not, even with undefined sub-expressions, is actually emphasized by Simon Cochin. And this is what gets us to exclusivity. So the Adana's, as we heard mentioned earlier in the graph theoretic approach, exclusivity graphs play a central role, and Adana's emphasized the importance of an exclusivity principle, which is formulated probabilistically. So here I'm going to talk about a logical exclusivity principle at the level of partial Boolean algebra. There's a lot to say about the relation between the logical exclusivity principle and the probabilistic exclusivity principle. It's in our paper, but I'm obviously not going to talk about it now. Anyway, we say two things are logically exclusive if they imply contradictory information. They may not be compatible, but you can get from them to things that are direct contradictions of each other. And you can think as an example, when you have just assignments of values to variables or observables, the one says that some variable gets, one event says that some variable v gets value 0, and the other says it gets value 1. That would be an example of something that would be logically exclusive, even though they're somehow the variables that they mention are not all compatible. So, right, so we say that a partial Boolean algebra satisfies a logical exclusivity principle if any two elements that are logically exclusive are also commensurable. This is a logical version of what's usually formulated as the probabilistic exclusivity principle. And in fact, it turns out to be equivalent to something that has been studied in partial Boolean algebras, the idea of transitivity. I'll just say that for P of H's, they always satisfy this property. So imposing it is a way of getting closer to the P of H's, which are the things we're really interested in. Okay, well, all right. So technically, we can again play around with our basic construction and find a way of forcing a given partial Boolean algebra into a richer one that satisfies this logical exclusivity principle. I won't go into the details. Having done that, we can define a stronger tensor product by forcing logical exclusivity to hold. So we get this kind of box times tensor product where we start with a weak one, and then we force logical exclusivity to hold. And this is sound for the Hilbert space model. Everything satisfied in here is satisfied in the Hilbert space model. So it's still a Lax-monoidal functor with respect to this tensor product. Of course, the hope was, could we hit the full Hilbert space tensor product in this way? And the answer is, unfortunately, that we get closer, but we're still not there. In particular, we can show that if A and B are not Cochin-Specker, A box times B is still not Cochin-Specker. Remember, the thing we want to grasp hold of is this emergence of non-classicality, that we go from C2, P of C2 classical, P of C2 classical, but P of C2 tensor C2 not classical. So we haven't found in this construction the right thing. Now, I'll just finish up with mysteries of partiality, just to show you how sort of rich this notion is. It's a standard fact that every finitely generated Boolean algebra is finite. You have normal forms, disjunctive or conjunctive normal forms. But something very, very different is true for partial Boolean algebras. And actually, in P of C4, there is a set of just 5 projectors, essentially the local Paulis, which generate a uniformly dense infinite subalgebra of the whole of P of C4. This is a sharper version of the result I mentioned earlier. So it's not only infinite, it's uniformly dense. Essentially, if you think of the unit ball, you're getting within epsilon close as you keep adding terms, as you close up under the, and this is only, I remember, under the partial Boolean algebra operations of commuting product and complement. So it's quite a remarkable result. And they use, I mean, this is Conway and Cochin, and they unfortunately, there isn't a full paper on this. It's a sort of report of a lecture. And they use some very elaborate geometry and algebra. I really wonder if I would like to have a more logical or combinatorial proof. Let me just finish up. There are various directions to take this. Something that Rui and I are currently working on, I think making progress with, is a kind of stone-type duality for partial Boolean algebras. Not exactly the traditional stone type. It can't be, because that's based on extracting points from a Boolean algebra, and Cochin-Specker partial Boolean algebras have no points, have no two-valued homomorphisms, but something relating to the duality for complete atomic Boolean algebras in the atomic case. And I'm fascinated by the idea of characterizing which contradictions can be realized in quantum mechanics. I've already emphasized axiomatizing the tensor product, and I think there are also interesting connections with understanding how to move from state-dependent to state-independent contextuality. And for further details, there's a paper which is appeared in a conference and is available on the archive. Okay.